Okay, okay. Let's start. So let's start with first of all, what is the inversion? Yes. So okay. So there are like some. Uh, let's go with like the easy definition. So first of all, you can consider one circle. Call this circle omega, and then you consider center of circle r. Let's assume the radius is r, small r. Then inversion is type of transformation. First of all, what is transformation? Transformation is like transformation in plane. Is like you take one point and you send it to another point, and you do this with all of the points on the plane. So that's what we call transformation. So inversion is a transformation where suppose you take some point. Suppose I take this point, call it A. And now I am going to send this point A to some point called A dash, and with some two conditions. First of all, uh, suppose this point is here, or not here, A dash, such that, first of all, A dash should lie on OA. So A dash should lie on a line joining point and center of circle. Also, this inversion is with respect to omega. So like you for omega you need a center and you need a radius. So each inversion like varies over like what circle you're choosing with which radius. And another condition is that uh, OA into OA dash should be equal to R square. Or some people like to write it as a OA dash equal to R square by OA. Uh, Now, with this kind of strange kind of condition, this transformation become very awesome. So, first of all, okay, yeah. So first of all, let's go with some examples. So suppose consider some point B here. Where will this B point will go? So this distance is R itself. So the B dash like O B should equal to R square, but this is already R. So this has to be R. So that's supposed to mean B is equal to B dash if B lie on the circle. Okay. Now let's go with some interesting one. Suppose you consider some point C here. So where should that C dash should lie? Like you should have some good intuition about like where the inverted point go because that will help you visualize the problems later on very easily. So what do you guys think? Where will C will go? We know that like if C was C like lie on circle, then it will like map to itself. But if C does not lie on circle, but it's like slightly inside the circle, and it should also go like inverse proportionally slightly out toward the circle. So it will lie like C dash here. And this gives like if like some point D lie here closer to the center, then it will lie like farther from the circle because like OD equal to OD into OD dash should equal to R square. Okay, everything clear? Any doubt? There is actually one point. No one asked me where will O like go. So let me tell. So for now you can assume O maps to uh, infinity because later on you will see like if you have something like goes to infinity, it actually get maps to O with inversion. So we will like put that in mind. Now, there is one nice property about inversion which make it very powerful is like if you now do the same process with A dash will go to A because A lie on OA dash and OA dash into OA equal to R square. So like in inversion, these two like if A go to A dash, then A dash will go to A. So this property preserves the niceness of the inversion. Let's start with proving some properties. So first of all, consider this circle omega, and now consider some 2 points AB, and now we consider their images. So they will look something like this. Suppose. Okay, okay. Yes. So first of all, okay. So now A dash is image of A, B dash is image of B dash B. Uh, so what do you have? We have that OA into OA dash is equal to R square, which is equal to OB into OB dash. So so if you guys like know like remind about like power of point, this is basically power of point. Like from point O, the power of this thing is equal to this. So this just by like conversion of power of point, we get B dash, A dash is cyclic. Everyone clear with this? Because like this is just follows from definition of inversion, and then we use the conversion of power of point. Now this is very interesting property because we, as we got like this is cyclic, so this angle, let me change color. This angle is equal to this angle, and this angle is equal to this angle. And this is very like handy tool because like whenever you invert the diagram, you always have to work with the angle condition, and you will see like actually you will deal with many angle condition which you should like get hand on. So this is the first nice condition. And with this, like if any of you want, you can actually compute what is like length B dash A dash. Uh, does anyone see how you can do it? Till then, I will give one buffer problem to whoever want. Mm, for this, right? I can't copy the source. Okay, it's fine. Okay, so the way we do this problem is like we first of all notice that this triangle VO dash O dash V is similar to triangle OBA by angle, uh, and then we use the ratio. So basically, AB by OA is equal to A dash B dash by uh, OB dash, and then by just rearranging some stuffs, you get that AB times. Now note that this O dash B dash is actually equal to R square by OB, so that's why you can write this as a yes, and this comes handy. So there's one like some IMOP2 which like you can just trivialize by because you know this length condition and inversion, and we will see the magic. So let's start with one question. Enough yapping now. Let's do some questions. Uh, let me why why not wait? Okay, so let's start with this question. Okay, so I will give some 1 minute to think and like tell me if you have solved this question or like have if you haven't, then tell me the ideas. Just say it if you want. It's fine. Okay, let me explain the question. So you consider triangle ABC with point P inside, such that this condition follows. Angle APB minus angle C is equal to angle APC minus angle B. And then if you let some D and E be in centers, then to those points, those three lines concurrent. Yeah, okay, sure. Anyone have any ideas who haven't seen the question before? Also, like, tell me if it's going too fast or too slow or something. Mm, okay, I will you start again. So first of all, this angle condition seems weird. So let let's suppose this is equal to k. Then this is telling us angle APB is equal to k plus angle C, and angle APC is equal to k plus angle B. And with that, only with this condition, you are they're asking you to prove that this point BD, C, and AP concurrent. Suppose at X. So first of all, like actually, you need to just note that like actually we are not using like B as an in center. Only thing we are using is like line B and line C, which are basically like angle bisectors. So actually, like we don't use much about in center. We just use that B is angle bisector, C is angle bisector. So suppose if they meet at point X, that's supposed to mean like the biangle bisector property xp ax by xp is equal to ba by bp, and that should be equal to ca by cp. So we don't know this, but so what we actually have to prove is that this condition. Once we prove this condition, then we can just say like suppose like this angle bisector meet at x, and by ratio condition, x should be intersection of this angle bisector too. So how are we going to prove this condition with this angle condition? And let me start. So first of all, notice. So we have to use inversion, of course. And the takeaway here is like don't always need like some nice inversion circle. You can work with like you can just sometimes use some random radius circle. The thing you only need to do is like work with angles and some properties. So the way we do this, okay, weird. Okay, yeah. So way we do this is we consider some circle around A. Suppose this circle is omega with center at A. And now we take inversion image. So once we take an image of this, uh, like suppose like okay, it will go something like this. So suppose C maps to C dash, B maps to B dash,
Wait, we
C
can
maps
like
to C.
invert about A and like get like B star equals B star C
Yes,
star.
yeah, exactly. That's what we do. So we invert about A with some circle with some random radius R, and called like this omega circle. And when we invert, suppose B go to B dash, C go to C dash, B go to P dash, and then this angle condition. So this angle is supposed to be some K plus angle C, which will, as we know that if this happens, like something like this angle will go to there here by cyclic condition, as I told. So actually this angle is now K plus angle C. Yes. But note that this angle, angle C, will also like map to this angle, angle C. Actually, let me try to draw this at the,
Actually, I think like we can say angle P
yeah,
prime B prime C prime is equal to P prime B prime A prime minus A prime B prime C prime.
yeah, exactly,
And,
yeah.
and
So,
that would be equal to what? Angle BPA minus angle BCA.
yes. So like if you consider B dash P as an image, then this angle will be angle C, and this angle will be K plus C. So that just imply angle P dash B dash C dash is equal to angle K. And similarly, you get this whole angle is K plus angle B, but this angle is just angle B because like again by cyclic property. And so that again imply angle P dash C dash B dash is equal to K.
So then P
And
prime B prime is equal to P prime C prime.
yes. So P prime is equal to P prime C prime. And now you have length condition. And we have worked with length condition. What we do with this length condition? We go back to our original problem. So these two condition implies that B prime C prime is equal to P prime C prime. So now by length condition, this should be equal to BP into some R square times AP into AB, and this should be equal to PC times R square AP into AC, right? Now R square cancel, AP cancel, and we get like uh, EB by AB equal to PC by AC, which is equal to this. So what we do, we find that like P dash B dash equal to P dash C dash. We do this length condition, we get this ratio. And as we get this ratio, we can just say that now if you consider angle bisector of this intersect at X, then by ratio condition, angle bisector of PCA also should also intersect at X. And so we are done. So now you see like we can like use some angle condition very smartly and like length condition using inversion. So this was first problem. So now let's move on to some more theory. Uh, okay, yes, we can go on some nice theory. So now you should wonder like why we actually like doing this because we can do some angle chase, but what's the actually point of the inversion? So let's look into why we actually care about this. So consider some circle, and we till now we just working with points, but now let's work with lines. So consider some line L. This is circle O, circle omega is center O. And so now let's think about where will this line map to. And you start thinking, maybe some random or it maybe comes out to be something very nice. So first, suppose like where you will begin with. That's the first thing, right? So one of the like obvious intuition, like not obvious, but like you will get intuition that let's draw a perpendicular from O and call this point P. And now like this is a kind of unique point because we're dropping perpendicular from O. Suppose the image of P is some P dash. Okay. And now we know that like if you consider any point Q on this circle line, then it should map to some point here, Q dash, such that this angle should be 90. Because we proved that like this P dash Q dash should be cyclic, and because this is 90 always, this this will be cyclic, and that cyclic implies this is 90. Angle P dash Q dash O is 90. And that is basically the circle with diameter OP. So like if you consider any point on this line L, like any point here R, it should map to this point circle on diameter OP. Because like only then if this will be 90 and because this is 90, they will be set. And if you consider reverse, like any point on this circle, it should also map to the line. And if you consider the point of infinity over this line, it should map to O. This kind of hard to see, but uh, so infinity maps to O basically. Yes, so circle will map to line, and because this is involution, like A point maps to A dash map to A. Uh, Point of infinity is like because this line will go at some point here at infinity, and like same here. The actually like you can actually see like these two infinities actually consider only one infinity. But yeah, but let's not talk about projective here. So yes, so line will match to circle, but sometimes like not always. So there's some side cases you have to work on. Suppose line pass through center, like this is O, and this line pass through center. Then we know obviously these points will map to itself, and any point on this line should match to some point on this line. So this line L will map to itself. Like this is not like each point will map to itself, but the set of points on the line will be mapped to set of points on the line. So basically line maps to line. So these are the things you should remember. So line map to line if it's passed through center, line map to circle if it's not passing through center. And there is one more thing. Suppose you consider also like so more important point here is like consider any circle passing through O. That circle should map to a line. Here you can see like it should pass through these 2 points because they map to each other. So like any like if you consider this small circle, it will lie to here. If you consider this some big kind of circle, it will map to here and so on. Like line maps to circle, circle maps to line. But there is a catch. Catch is suppose you consider some circle like this, which do not pass through center. Then like consider suppose this center is O dash and you draw a line. So if the point is A and B, they should map somewhere here, right? A dash, B dash. And suppose consider any point C here. Then here we're going to use like very nice thing. So if you consider C dash as the image of C, then you can work on some angle. So you know like this, they are cyclic like A dash A, C, C dash cyclic, B dash B, C, C dash cyclic, again by power of point and cyclic condition. So you get that this angle is equal to this angle because of cyclicity. Let me choose some other color. This angle equal to this angle, and this angle is equal to this angle, which like which actually give us like this angle is always equal to this angle. Whether like this is center or no, like this is like very important condition. Like if you have 2 points on same line and if you map it, then like any other point, the angle will be preserved. That's like one of the important property that angles will be preserved. And now, now if you consider center, then this will be 90 and this will be 90. So this should be like circle with diameter a dash b dash. And so this gives like circles map to circles, but like if they are not passing to center. But here is one thing you should know that centers do not match to centers. Uh, that's because like the condition about like inversion is like inverse proportion. Like AO into AO dash is equal to R square. So now we're considering midpoint of A and B as O dash, but it does not necessarily means like it should map to midpoint of A dash B dash. And later on you can like see by like some angle chase. Like if you consider tangent from this circle, from O to this circle, it will intersect at image of O dash. But it's fine now. For now, the important point is like circle, if circle pass through center, it will map to line because of the 90 condition and so on. Circle will map to circle and center do not has to be preserved. Okay. Uh, Everyone fine with this? Anyone have any doubt? No. Okay. So let's there's one more interesting condition like to think about. Consider circle again because all we do is consider circles and consider intersecting circle. So in general, wait. This is something. Yes. So this will map to circle again. Yes. Uh, okay, I will buffer problem. Okay, I will show some buffer problems because many of you requested. But not that buffer problems are hard and they may be really hard. So this is one of the problem. Take a screenshot and also try 1215 E3. I don't know. And maybe I can give you one more problem. Same list of problems. Okay. Take a screenshot for buffer problems. But we will start doing like nice problems too. Okay. So, okay, everyone clear with whatever we did till now? Yes. Okay. So let's go over this another property. So suppose some circle intersect like our omega at A and B, and it has nice property like now you know A will map to A, B will map to B, but it has nice property that AO is tangent and OB is tangent. So what does that do? Suppose consider any point C on this, then if you know like by tangency condition, it gives us like AO dash equal to AB dash equal to AC into AD. This is the D. This is true because like if you consider any point outside, by power of point we know that this O is here and this is D. Then OD square is equal to OA into OB. This is power of point. So by power of point we get like OA square equal to OC into OD. But note that OA square is R square because this is R. So like if you consider image of C, it should be like D only because OC into OC dash C dash equal to R square, which is basically OA. So C will map to D and there's nothing special about C. So you consider any point other than A and B on circle, it will map to like this intersection. Like again, like the major arc will map to minor arc and minor arc will map to major arc. And that's just awesome because like now the circle is actually not moving. Like this circle, whatever you call it, gamma is preserved, and that's like ma- one of the nice property about inversion. Now you preserve the circle. Now you can like do many things, and by many things, let's do some nice problem. Uh, which is like one of my favorite problem. It's looks so sweet and simple. Yes. Um, I will give some 2 minutes, and any of you seen it's fine. But if you have never seen this, then give us the ideas because this is very nice problem, and this will show you how why we use inversion at any place. So like on chat or something, like ask me doubt if anything is confusing or something. Second statement. Okay. Maybe I will draw the diagram. So there are like first circle omega and omega 2 tangent externally at P and also internally tangent to some another circle. Oh, this is so bad. Okay, every line passes. Oh wait, okay, I will go over this, but let me just okay. So this is omega 1, omega 2, and this is big omega, which is tangent to this small circle internally at A1 and A2. And point P is a intersection of common tangent. So consider common tangent at P intersect at P. Then you consider this line, and I'm drawing this variable vertex line in this second line. This is B2 and this is B1. Yes. and you have to prove that this interesting line is actually tangent. Okay. Uh, okay. Um, okay. Yeah, but like I'm not sure. Like the way I saw it was like just reflection. Like I don't remember like using inversion. But probably at now you say probably we can solve it using inversion too. Yes. Also, okay. So um, some people can work on this problem, and till then I will explain like one of the important things. So what? So now you know like point on circle maps to point on circle, interior point maps to exterior point on the same line. And now you see if you like take this point very close to center, this point image will go very outside. And so if you consider like very close to center, this will go like very far, like at the infinity of this line.
Yeah, limit
So
infinity. Yeah.
yeah. So now there's another concept. So for like if you consider this line and like all of the parallel line, you consider like like point at infinity on this direction. This is like one point of infinity. If you consider this line, then there's another point of infinity. This is like infinite discussions. Yeah. So this O will map to this infinity now. And now if you consider like this another line, then for that infinity, it will again map to O. So all of the point of infinities will map to O. That's how it works. Because like however you take point close to O, it will like go as far beyond. So that's why we consider that. And if you want to know, so this is like projective condition. Like generally two parallel lines never intersect, but we assume like all these parallel lines intersect at some point called point at infinity. And like for different direction, different orientation, we have different point of infinities. Yes. And like if you take some kind of projective map, then maybe like you can consider all of these points and like you get like line of infinities, like all the points of infinity lie on one line of infinities. Yes, Alan, Alan
I
Prashant.
was telling like the point of infinite, like inversion is a bijection. So if all the point of infinity is matched to O, shouldn't like all the point of infinity be same? Because this is essentially a bijection.
Uh, True, but let me think. Yeah, like if you go like official definition, where we actually like never consider like image of O, like you do not consider image of O because as you said, it's not bijection. So like this nice transformation doesn't preserve bijection, but we want bijection work because it's like only exception at O. So yes, like it's bijection except O, and for O, we assume that it's maps to O, infinity, because that intuitively makes sense, and that's how it should work. But like officially, like if you go mathematically, we actually never define the image of O. We like take all the image but except O.
Yeah, makes sense.
Yes. Okay. So let's come back to this problem. Um, so what we given? So we given like these two circles, omega 2 tangent at t, and we have another circle omega which is tangent at a dash and a2. So now, okay, so how we actually proceed? Like, suppose you want, like, when you actually use inversion. So there are some nice like you will get intuition as you work on, but some common intuitions like if you have some point and like so many circle passing through that point, then you invert at that point because that's like most useful. And if you have some tangency condition, then like if you invert at that tangent point, then they will go to some parallel lines and so on. So that's also good condition. And like if you have some nice circle, like some common radius circle, then you know. So here, like, we know that PT is tangent, right? So where like what are the points where we can invert? And not like we want this like some line, like we want this common tangent, and like B dash and like B2, B1 and B2. So anyone have any idea about this? Hmm, okay. So where we go for it like, so this is PT is one of the tangent for omega 1. So consider like, suppose you consider another tangent from P to this omega. And if you like, suppose this is X, and suppose consider another tangent, this is Y. Then because like we are considering tangent from like one point, then PT equal to Px equal to Py. So that just like, you're like, oh, excuse me. Um, that tells us like this circle with like circle center at P with like PT radius is very interesting. Like uh, it basically tell us like this will preserve omega and omega 2. As I told you, this will preserve omega 1 and omega 2. Because this condition is same. Like if you have center and like if you draw two tangent and it intersect the circle at that point, it should preserve this gamma. And we call this like if this is omega, then omega is orthogonal to gamma, and we denote it by like this. So like similarly, if you here like consider this circle, okay, then call this circle something like, I don't know, like what do you call it? Yeah, call this gamma. Then this gamma is orthogonal to omega 1. Gamma is orthogonal to omega 2 because like gamma is basically like circle center at P with PT radius, and because PT is tangent to omega 1, then Px is also and Py is also. So that means we preserves omega 1 and omega 2. So if we consider image of A dash, A1, because that's the point we have on the question, then it should map to the intersection of P1 with P, which is basically B2. So A1 will map to B2, B1, sorry, and A2 will map to B2, right? And that's the one part. But there's one more circle, which is like omega. Uh, so where will omega maps to? So the
Can you
way
again
we,
explain why did A1 map to B1 and A2 map to B2?
yes, so we know like omega, like omega, sorry, gamma is, okay. Gamma is orthogonal to omega 1, right? So gamma,
Yeah.
like, so inversion preserves omega 1. So this A dash point should map to some point which also lie on omega 1 and lie on line
Oh, okay,
E,
makes sense. Okay, I got it.
yeah, and which is basically B1, right? Yes, and yeah, because this is orthogonal. And now if you consider image of omega, so this is how we generally like see the what where image go of circle. So we know like A1 and A2 lie on omega. So the image should contain like image of A1 and A2, which are like B1 and B2. And one more thing is like E passes through omega, like P lie on omega. And in inversion, if there's circle passing through center, it should map to line, basically. So this should be some line containing B1 and B2. Uh, do you guys know like what is the line passing through B1 and B2, 2 points? Yeah, surprisingly, it's basically those 2 points connecting each other. Yes, so if this is like, and it should be also like gamma intersection omega, like these 2 points should be preserved because like they are same radius. So this is like image of omega, omega dash, which is like line B1, B2. So image of omega is line B1, B2. And now now we use the condition that omega 1, yeah, omega is internally tangent to omega 1 and omega 2. Like the tangent here. And okay, this I should mention, but inversion preserve tangency. Can you see why? So if you have some like two lines of circles, like lines of circles are interchangeable in inversion. So if you have two lines of circles, and excuse and they intersect at 2 points, then image should also contain only 2 points intersection. So if you have some two lines and or like some circles, excuse me, sorry. Yes. So I'm saying like if you have a line or circle intersect at one point, like as someone mentioned, inversion is bijection. So that two image also should intersect at one point. So this gives us like if these two are tangent at each other at A1, then the omega dash and image of omega 1 should tangent at like B1. So that's basically like uh, this line omega dash is tangent to like omega 1 at B1. And similarly, like omega dash is like tangent to B2 at omega 2 at B2. So that basically tells like B2, B1 is tangent to both of the circles, which proves the thing. So does everyone understand like how we nicely use the fact and the orthogonality, right? Okay. Now, if everyone did this, yeah, anyone have any doubt? Uh, Now we can move on to like, if everyone is okay. Mm, so do you guys want to do one more question or like theory? So I will leave it on you. If you guys have any preference. We can do one more nice question, I am question, or we can do root based inversion. Mhm. Mm, root based inversion. Awesome. Okay. It's never get old. So now, okay, yeah, let me think, like, let me say everyone is on same page. Inversion is thing which maps circles to lines to circles, and it works very nice with them. It's some transformation. Okay, so now, like, we each time we don't have circle. Like, where is circle in the triangle question? So now I will I will tell you, there's very awesome inversion which actually like give us so many nice properties with circle, and we call it root based inversion. So first of all, so consider the triangle ABC. Uh, Let me say what is root based inversion. Root based inversion is inversion at point A with the radius root AB into AC, and along with like reflection along angle bisector or A angle bisector, which is like this. So, let's first think. So first let's just apply this thing. If we apply root BC, then this B should map to somewhere B dash, C should map to somewhere C dash, such that like B dash AB equal to square of the radius, which is AB into AC. And that just tell us like this AB dash is equal to AC, and yes, and AC dash, as you can guess, is equal to AB. Yes. Now, because like we have some nice like AC dash is basically equal to AB. So if you reflect everything about A angle bisector, we know A angle bisector is like bisecting angle AB and AC. So it will actually map like C dash to B and B dash to C. So you will actually like after like doing this whole transformation, like first inversion and reflection, you actually like getting like B maps to C and C maps to B. And yes, so so seems like a nice property because like you can get so many more things. So consider the circumcircle like ABC of the ABC, and where will it will map? So it passes to A. So whatever the like circle we are considering, it passes to A, so it should map to some line, and it should pass to B and C. But B map to C and C maps to B. So that just give us like AB maps to BC. Like this circumcircle maps to BC. And these are like things like actually define like this inversion nicely. So if everyone understand this transformation, let's like work like some nice property of this. So let's first like see where will these two things map or like lines. So now we have this circle, and we don't draw like so. This circle is basically this circle here with like root BC radius, and then you do reflection on angle bisector. But whenever I say root BC, just you just like consider like it's supposed to mean like you take inversion and reflect. So now we have ABC, and now consider circumcenter O. Then we know that like this angle is 90 minus B. You can work out because like this angle is angle 2B and these two length are equal. So it's 90 minus B and this is 90 minus C. Right. But as you may have noticed, like there's one more interesting point on this like line. Okay, I will remove this for now, which is like H, which is orthocenter. And orthocenter have like this is 90 minus B and 90 minus C. So this tells like H and O are like isogonal to each other in this angle, like the reflection about angle bisector. And what feels like nice to this is like if you expand this point, and we know this is like antipode of A, and if you draw the theta perpendicular, then D will map to A dash. And way to see it like so like where BC maps to ABC, and we know that like this line AO will map to line AH. O does not map to H, but like line AO will map to line AH. So like because D lie on AO, it should lie on AH such that it should lie on BC also. So like those are like just two things give us like B maps to A dash, like antipode maps to feet. And so you can like if you have some problem along like A dash, you can work with like D. Then there are some more things. Yes. So consider like midpoint of R. Call it now what M no N. Yes. Uh, can you see where it will map to? Yes, it will map to this point L, which is basically like intersection of A and like angle bisector with this. And these are like nice condition because like if you consider like this another midpoint of R, this should also match to like line passing through A here and so on, and like we have some nice condition with root BC, and like this inversion is like very like nice to be considered. So now let's just work on one problem to like actually get feel what are you doing. So this is the way we learn things by Russian problems. So here's a Russian problem. And okay, uh, yes, let me tell if someone don't know. Median is basically like reflection of median along angle bisector. So if M is a midpoint of BC, then like you consider reflection of AM along angle bisector and you call it a C median. Let me see how much time I have. A lot of time. Yes, so, so I will explain the question, and then like now I want like you guys to like come up with idea because that's how you guys need to learn. Okay, we are angle bisector intersect at D and again at E. Huh. Then with diameter geometry intersect again at F. So first of all, like notice like uh, if you know like this is midpoint of arc, right? Like angle bisector intersect at midpoint of arc, and so this should be like if you consider midpoint M is the midpoint of BC, then ME should perpendicular to BC because like E is midpoint of arc, and so like M also should lie on like circle with diameter A, but M does not lie on omega of course, so they are considering other point F. And now we have to prove like AM and AMs are like isogonal, like basically the reflection on our angle bisector, and AD is basically angle bisector. So yes, so what we can do, uh, anyone want to tell, say, uh,
Okay, so under root BC, D would go to E.
yes,
B and C, I don't think we really care.
okay, so we do root this inversion, which is inversion with reflection. So
Yeah.
B will go to C because we do the definition. Then circumference ABC will go to BC, and because like we lie on angle bisector and circumcircle ABC, E will go to D because D lie on BC and on that line, and angle bisector prism angle bisector. Okay, now we have to think where will this circle with diameter D will go. We know circle goes to circle, so it's some circle. We also know like D and E should, yes, yes. Do you have, wait, someone was saying something? Okay, so we know like the circle should like contain point image of D and image of E, which are D itself. So it should the image of this diameter circle is another circle passing through D and E. But we have another fact, which is like we know like if you have some circle, wow, what else? Yes, and you have some another circle, and this is the diameter. Then the image also like for image, these 2 points are also diameter. So this like if you consider this circle and like any point here, and like image of this is just E, D, and like this point, suppose M dash, then it should like also be 90, and that just give us like the circle will map to itself, and which is basically equivalent to like this is orthogonal. So this circle with D, we denote like diameter like this, is like orthogonal to like just omega, like small omega, I mean, whatever, like just inversion. And now we're doing like reflection about angle bisector, but D is a diameter, so reflection will just preserve the same circle. So that just tell us like this circle maps to itself. It's like orthogonal. Okay, right. So basically so that gives like F will go to some point. So F lie on ABC, so F will go to some point on BC, and F lie on this circle, so F will go to point which is another intersection of this circle, which is M. So this like just by observing, we get like F max to M. And because like this inversion is like inversion with reflection about angle bisector, these two should be isogonal. So these two angles are same. And we prove that A of is median. Does everyone understand how great is this?
Yes.
Mm, yes. Now I wanted to cover one more problem.
Does the F point have any nice name? Because it seems like a nice point.
Which point?
The point F.
Uh, A S. Wait, what's the S again?
I meant F, the point F, the inversion of M.
This okay, this F, okay. So yes, so if you like explore more like when you learn about like wait, okay, learn more about projective geometry and harmonic, then you will know like this is like harmonic point. So we get like this A B C are harmonic, which is like basically means like tangent at B and C. These three lines are collinear. And actually like the one easy way to prove this is by like suppose tangent at B and C intersect at T, then you can prove A, F, T are collinear. An easy way to prove is by using the inversion, root BC inversion, because which tangents will go to like like circle of C tangent to this thing, which is like this, and with another is like this, and this is called Humpty point and so on. This is like very rich configuration. But yeah, but you
How
can
do
like
you how do you prove AFBC is harmonic?
uh okay, this is another lecture, but when this like because this is like reflection of AM, so it's like symmetric, and as I told, like once you
No,
throw
no,
like
no, no,
this,
no. In this problem, like how do you prove?
we don't need the this thing. I'm just talking outside problem.
Oh,
We don't need problem, right? Like AM is symmetric. Okay, now as a like the root BC is an interesting inversion. There is another like equally interesting inversion, which is like root BC by 2. Actually, okay, because we also have to cover one 3D geo. I will not do this problem, but I will put this in like at problem set. But if anyone want hint and anything, okay, we can do one simple problem if you guys want. So, okay, yes, there's one simple and like nice, but like very nice result. So I want to cover that problem. So let's go over that. Okay, let's do this one, which also include like very nice inversion. And this is not so hard problem. Alright, give me some. Okay, guys. Idea. Okay, let me explain the question. So you have like in circle. So in circle touching the side of ABC at M and P. Uh, okay, yes. And then like your in center I, your circumcenter O, and all this. Oh my God. Inside this perpendicular, and yes, this should be suppose orthocenter. Suppose H is orthocenter of this circle, and we have to prove like H, I, O are collinear. Collinear. Yes. So any idea? So first of all, I hope like everyone know about like Euler line, which is basically like if you are if you are triangle ABC, then if you have circumcircle O, orthocenter H, and then centroid G, then these 3 points are collinear, which is like very nice fact. And one more nice fact is like the 9 point circle, like circle passing through midpoints and heat of altitude, and N, like we call it center N. These 4 points are collinear. If anyone you don't know, like very nice things to prove and very nice practice for angle achievement. Things. Yeah, so this something sounds very similar to this. Like we are at the center of AMN and I is basically so in center is basically circumcenter of AMN. So we have this Euler line of this triangle. Uh, and okay. And we want to like prove that O line on this triangle. Yes. So do anyone have any ideas? You like give me 1 minute because I need to put my laptop on. Yes. So does anyone have any idea or observation, anything? We want to prove like rely on like Euler line of triangle AMN, ANP. So first of all, how we going to use inversion? So root BC doesn't work here. Uh,
In circle
so
inversion?
in circle inversion, exactly. So I want to like emphasize like you can actually invert about in circle. So if you call this in circle omega, then we invert about omega. So center is I, and let's see what happens. Okay. So let's try to explore. So M will go to M and P will go to itself. Then where will A will go? We know that like
Point of PN.
yes, because these two angles are 90 because it's a feet. And so like this whole thing is cyclic, like A and IP. This is cyclic. So and I lie on it, so it should go to some line, and this line is precisely PN. And if you draw this line and call this A dash, then like because like it's symmetric, AP equal to AN, we get A dash is midpoint by symmetry. And basically same happens with everything. So B dash is midpoint, C dash is midpoint.
So the circumcircle goes to the 9 point circle.
Yes, exactly. So suppose this is like circumcircle of ABC and it should map to like in the image of the points of course on the circle. So circumcircle will map to its image which is A dash, C dash, C dash and uh, this is 9 point circle. So 9 points it's 9 point circle because like A dash, B dash, C dash are midpoint of side lanes of ANN, MPN, and 9 point circle is precisely the circle passing through midpoints. So now we know that like the, the image of ABC is actually very nice. And this is like very nice fact to like know because like if you like once you start working with like hard configuration in geometry, a lot of times you actually do inversion about in center and a lot of times you use like this in center inversion. And okay, so now what we have, like we have the 9 point circle. So if you consider center of this 9 point circle, suppose the center is N, then N should lie on Euler line of this triangle. So that imply like N lie on this line A. Yeah, right. And another fact we know is that like if we are like if we have this circle omega, this circle will map to this circle, some circle. Center do not map to center, but we not know that like center will map on line. Like if this is O dash is suppose P is P is the center, then it should lie on line P. P dash should lie on line OP. So that just means like O, the image of O should lie somewhere here, O dash. And um, wait, yes, image of O should lie somewhere, but also like the center of A dash, B dash, C dash should also collinear with like, so N, I, O dash is collinear or O. Because like O is the center of ABC and N is the center of A dash, B dash, C dash. Center do not match to centers, but they lie on the same line passing through the point of inversion, center of inversion. So this gives us by center, this is proved by Euler line. So that just imply H like N I O R collinear. So these things are collinear always, which is very nice fact to work with. So does everyone understand? Hmm. Okay. So we have 15 minutes left. We can do one easy problem or we can go for like 3D geo. I guess 3D geo should sound good.
Video.
Yes. The clickbait of the lecture. Um, okay. Now, okay, this time I'm like seriously saying like you guys going to solve this problem. I'm not going to, but I want to specify something like now this is 3D geo. Let me tell what actually inversion looks in 3D. So in 3D, you have sphere. So consider this sphere and suppose this point O here. And like now you invert about sphere uh like okay, suppose another sphere which is like something like this. Wow, parameters. Yeah. And now this is omega and this is gamma. And now if you invert about this omega with center O, because O lie on this gamma also, each of these points is basically like this point will intersect some point here on this plane. And because like gamma pass through O, the sphere will map to plane. Now spheres map to plane and plane maps to spheres. So all of the points on this like sphere should match to like this plane. So let's try to visualize if you have some point and like consider any radius and like any sphere that should match to like plane now. And like not POP, but like the here we don't precise in the cyclic condition, but the definition is same. Definition is like image of A should be A dash such that this is true. The R is some constant, and like it should like this should be collinear. Right. Okay. So with the now you know this thing. Now let's see how you can tackle this question. Okay. Now first of all, like okay guys, idea. Till then I will try my best to draw this figure. Hmm, I don't know how you do this. Wow, beautiful. I actually can't draw it. Uh, this, but okay, let me label. Hmm, this, image. So tetrahedron is basically like the pyramid type of structure, like each face is triangle, and we have four vertex. Then we have like ASP, then there's sphere whose center, like suppose this is center lie on this plane and it passes through A, B, C. and it intersect like this segment SA, SB, SC again at A dash, B dash, C dash. And now to this sphere, also it's hard to draw. So like try to imagine like you have this sphere, and now like if you draw all of the planes, like there are lines, but like all these planes which are like tangent to sphere will intersect at some point over here. So let me just clear things like this is a point O. And what we have to prove is like O is the circumcenter of like S A dash B dash C dash. Call this dash rather than B1 B1 C. This doesn't matter. This yes. Now I guess guys. What are you going to do? So we have some sphere which passes through like 6 points, and then we have tangent at some 3 points in the intersection. So probably like uh, you never work with, but okay, I guess like because of time constraint, I maybe start. Okay, I will give some more time. So the way you go with it, like because like like what you do at like 2D, like your power of point, right? That's what you basically use in inversion. What do you think about this? Like the how will PowerPoint work in 3D?
Power of line.
No, but it's not like it's basically same. So what I'm saying like you can actually like work with like PowerPoint same as like sphere. So if you have some sphere, suppose you have some sphere, this is a point, and you intersect this at 2 points, like this, somewhere like this, and like imagine it's like going through the sphere. Then like this length A B S, so SA into SB is like power of this point with respect to sphere. So it will be the constant. And that what I'm saying basically is that because this A dash, B dash, C dash, A, B, C lie on sphere, we have like AS into A dash is equal to AB into S, sorry, SB into S, B dash and S into SC dash, which is power of S with respect to the sphere, called the sphere omega S. So now you have this condition. So now obviously like what inversion we going to do? We going to invert our point S with
Root SA times
yes,
SA dash.
yeah. So suppose you call this like something like R square, then like this should be R square and the radius of sphere is like R, center at S, and we're going to invert about that. And because of the definition again, A will map to A dash, and B will map to B dash, and C will map to C dash. Yes.
What about the
And
sphere SA dash? The circumsphere of SA dash C dash B dash.
it will map to ABC plane
Yes, yes.
because the sphere passed through S and it should map to the image of the 3 points. Okay. Yes. So now what we have? So we got like where nice inversion. So let's try to decode the things. So first of all, what we given in question? What we have? What should we look for?
We have the sphere of like
No, like we have
ABC. Uh,
the sphere maps to
yeah.
itself. Like the sphere maps to itself now because we are also saying like it's orthogonal basically. Now we
Mhm.
have
Yeah.
planes. The plane at A dash, B dash, C dash, which are tangent to the our original sphere omega. Right. So let's try to think where will these the planes will map. So the what we have. So let's start it first, like one by one. So consider like plane, like you call plane whatever. So lambda. So lambda is a plane passing through A dash, which is like tangent to omega 1, omega at A dash. Okay, so it's a plane tangent to this sphere. Now A dash maps to A. So this plane should contain point A, and plane will map to uh, sphere.
Sphere.
Yes, and this plane do not pass through S. So that should imply like the sphere passing through S and A, uh, and it should be tangent to omega again. So this plane lambda we map to some like call it like omega A, which is like omega A is tangent to like it's tangent to omega because like this plane is tangent to omega and it contain point S and A.
Wait,
That,
why
that's
does it
what,
contain S?
because like it's a plane not passing through S. You know, like in 2D we have a line not passing through center, then the image should like have
Ah,
the
yes, okay.
circle should pass through line. So basically same, like if we consider this sphere passing through S and A tangent to the omega, image of that sphere should be some plane passing through A dash tangent
Yeah,
to omega.
point or infinity on the plane.
Yes. Yes,
Good.
point of infinity on the plane. Yes, it was. That's this really. So okay, everyone understand this thing, right? Like omega, what is omega A? Like where this plane will match to? Everyone, anyone, everyone. One more person, please. Now it's getting interesting. So now, similarly, we will have omega B and omega C, which are like s- sphere passing through SB tangent to our omega.
So, radic.
Uh, Something, but actually you don't know about radical, but
Yeah.
try to use, we actually haven't used one fact. There is something missing.
Um,
I will wait someone to notice it. So we use the intersection condition tangent of planes, but
all
they
eyes on
like,
ABC.
yes, all eyes
Okay.
on ABC. How are you going? So right now this like get more complicated. You know, like okay, I can't draw, but I will try. But I will ask you to like imagine everything. But so this is some kind of sphere we have, right? So okay, mm, so this is a sphere, and this is yeah. So it's like kind of sphere we have, and we have another sphere which is tangent to this, and like another sphere which is tangent to this, another sphere tangent to this, like this. Now, it's not obvious why it should intersect at one point, another point, but like we actually made this complicated. But the reason we making this complicated because we are now going to use the condition. Like, so what are the tangent sphere? So you have this one sphere, and you have this another sphere, right?
Wait, what is this bigger sphere?
Okay, so like suppose some two spheres are tangent to each other. This
Which
is
two?
omega and this is omega and this is omega.
Okay.
Yes, and they are tangent at A, right? Uh,
Oh, then you'll have
mhm.
something like that for B and C.
Oh wait, am I missing something? No, yes, yes. So yes, okay. But no, so now we use the fact that consider center of this, which is O, and consider center of this bigger one, OA, like center of omega A. And the way we use tangent condition is like these three should be collinear. Because
All right,
basically,
the three spheres will be at intersect at
no,
one point
there are
other than
three,
S.
there are two spheres. Like I'm
No, no,
considering this small.
if we take the other sphere, the omega B, omega C, and omega A,
Yeah,
those three, one will go at S. One intersection of all these three is S.
yes, they should intersect, but like, why they should intersect? Like, just not because radical, because it does not work like equivalently, like that. But
Right, right.
what
I'm saying that the only intersection is S.
that's not true actually. We have one more intersection.
No, what I'm thinking is something like on the other pole, like
No,
something.
no, okay, no, no, no. They intersect at A, B, C respectively, and they're only like the three circles have a common point S right now.
Yes.
Yes, yes. So now, okay. So let me repeat the thing. So we have omega, and like we have omega A, and they are tangent at A, and omega A pass through S also. And we know like the center of omega lie on this plane BC, ABC, and because they're tangent at A, the same thing work. Like if you consider homothency at A, which send omega to omega A, the centers should map to each other. So it's give us like O should match to OA, like this OA are collinear.
BOOBCO.
And
So
yes, and so similarly, like what we have is like OB. What? Okay, yeah, okay. OB are collinear and like OCs are collinear. So everyone see like how this also forms. Yeah. Uh, yeah. And now how we going to use this is like we know O lie on the plane ABC. So these are just line in the plane. So this imply like OA, OB, OC, all of them like lie on this plane ABC.
ABC.
Yeah, this is not correct notation. I am just making up stuff. Yes, but like all lie on ABC, and because we prove they are collinear by tangent condition, this all lie on ABC. So now we have like some sphere center lie on one plane, and one of the common intersection point is S.
So there'll be another pole.
Yes, we have the reflection of S about this whole like. So now you consider this reflection of S in the plane, which is S dash,
So this is
and like
reflection
eh,
S,
so yeah, so suppose okay, this is the plane.
but S is the center of reflection, right? Sorry.
No, S is like one of the one more point, like tetrahedron point.
Yeah, yeah.
Yeah. So like okay, suppose this is a plane and this is in 3D, like in space. Then you like draw a perpendicular and like you take like you go deeper. So it's like
Yeah, yeah.
yeah, like, better
Uh,
than
what was the sphere from what you were inverting again?
the sphere like at S,
Right.
which
So
is
S is the center of the sphere on which we are.
yes,
So
yes,
how can
center of
you take the
no, like the inversion is just for like to notice like there are some spheres passing through S and B and tangent to omega. Omega is
no?
preserved. Like
Right, but how can you take the
the
mapping of
EMF
S through
make
the inversion?
wait, how can you take?
Your S dash is the um,
No,
inversion map from S. How can you get that?
wait. So for like X go to X dash in the map, inversion
Yeah,
map. So we
right. So
actually
you're
do
saying
not
S goes to S dash.
oh no.
That's what
I'm
I was thinking.
no. I'm saying like okay, now you have this all three centers lie on plane ABC.
Yeah.
Uh, what you consider is this is a plane and this is like the center suppose.
Oh, reflection of S about the plane.
Yeah, reflection.
Okay.
So
Okay.
so this
Yeah,
OB
that
lie
will be
on
your
this
other
plane.
pole. That will be your other pole.
Yes. So like if this X is in like 3D space, then we know like these two are equal. And now if you like consider reflection of S about this plane, like we have this plane, S is here, and you consider reflection of S, then for any point in this plane, this distance should be equal.
That
Because
will
like
be the point once you get when you invert the
no,
intersection of
we
the
don't need to
planes.
it's just like S is reflection of S
Right.
in the
So, but that means S dash is also the
yeah,
invert of
I get
your
it, yeah.
O.
Yeah, yeah, that's we do it. That's how we do. So expression is reflection of S in plane ABC, and because like the centers lie on ABC, the like we get S dash OA, equal to SO.
Yeah.
Okay. Yes. So now you have like this equal to this, and like this similarly work for all of the centers, and that just imply like S dash lie on like omega A, omega B, omega C.
Yeah.
So S dash is another intersection. But remember, so what were like omegas, A, omega B, omega C? They are like the image of this plane, the plane passing through A dash, B dash, C dash tangent. So we found like they have two intersections. One is S, but S is center of inversion, so that basically like goes to infinity. That's why we're getting plane rather than sphere. And so another intersection is like intersection of those planes, which is precisely O. So
Yeah.
yeah, so that's like tell us like O is precisely the image of S dash in this inversion.
Yes. Yes.
Yes.
So you're
So
done.
uh no, wait. How do you
Yeah,
mean?
because the O, which O are you talking about? You defined two
Oh,
to
okay,
us.
okay, sorry. I mean ah name this R guys. Okay, never mind.
Oh,
I shouldn't name this O, but okay. Okay, name this O and we haven't used this point, so name this
yeah,
P.
R, P.
Okay, okay, yeah.
It's
P.
fine, P, P.
Yeah. So this P point, now like wait, how you finished it? Like we have to do like
No,
the
no, you said O, that's why I thought original O.
no. Actually O is like not the point. Okay, call this P now because we have already introduced O. So P is the intersection of three tangent planes and it will map to S dash, which is a reflection of S in plane ABC because like the centers are on ABC. Yes, that's all. Now because this is true, we have like S, P, S dash collinear, right? Now just consider one plane which contains S, P, S dash and B. Okay,
And
and B. So this is S, we have B dash, we
okay,
have
okay.
B, we have some point E here, right? And we prove that there is point S dash here,
Yeah, that
right?
plane. Sure.
Yes. So now we know that S is reflection of like in the plane ABC, S dash is reflection of S. Okay. That implies this is equal to this.
Hmm.
We know like B and B dash are image of each other and P and S dash are image of each other. So now we use angle chase guys. This
P.
angle is equal to this angle is equal to this angle, which implies PS equal to PB.
Yeah.
Yeah. So yeah, we just use these two angles, and this similarly can be done for other things. So we
So
get
you
like
have it.
yes,
Circumcenter.
yes, and this implies like P is a circumcenter. We are done. Okay. Anyone who any doubt like they did not understand from any like beginning or anything, just ask because I will repeat this once because this is very beautiful. So we consider sphere, and the first order power of point was same for sphere. Then we get like how you what you think or like what circle to think for inversion. And the one of the like best way to motivate is like if you have some power of point, like some common power of point, you invert about the root of that power and like consider that circle. So now in 3D we consider sphere and we get like A maps to A dash and C dash and so on. So omega is preserved. Then we try to conclude where will plane we map to, and planes will map to spheres and they are tangent to each other, right? Uh, yeah, so we conclude planes will map to sphere and like these are some like this sphere is tangent to this sphere which is like this C, B, A and so on. And then like because like these two spheres are tangent, the centers should be collinear with tangency point. That's imply like AO is like collinear, but like we know like O lie on the plane ABC. So that just imply like O and all these three centers of spheres, OA, OB, OC lie on the plane ABC. And now once we have this, you can imagine like this is flat circular plane and you have S and you take a reflection of S and now like any for any point in this plane, because it's like reflection, these lanes are equal. So for like any point, well, any plane, you take S and reflection S dash S. For any point R, these two things are equal. Yes. And so that's why like the H dash should be like intersection, like lie on all three spheres. So H dash is in another intersection. And we know that we define like O as O, like okay, not O, now we call it P actually. But we define P as precisely intersection of these three planes. So image of P is like H dash, which is precisely intersection of these spheres. And now we have this because they are like intersection, they are like inversion. So this thing should this is follows from first property of inversion. The image should be collinear. So we have P X dash and like B like this. And now these are like cyclic because just power of point. So this angle is equal to this angle. And because this length is equal to this, because again reflection, this length is equal to this. And that just imply like Ps equal to Pb dash. And similarly, we get like Ps equal to Pa dash and Ps equal to Pc dash. And that gives us P is a circumcenter. And that finished the problem. Okay? Anyone have any doubt or anything? So there's another nice geo, but I will put it in like a 3D geo, I will put it in problem set. But okay, anyone have any question related to lecture? Otherwise, we'll end the recording and stop the recording. And no, okay.
More
Yeah,
like I was thinking more about this.
yeah, okay, okay. We will talk. Yes. Okay. Bye, guys. Oh yes. Wait. Did I stop recording?
No, you stop presenting, not the recording.